So, as Hassan said, I'm Carlos Moro. I'm an assistant professor in Texas State University. Before starting, so my presentation is about the impact of CO2 uptake rate on the environmental performance of cementitious composites. That means that we are proposing like a dynamic global warming potential. So I'm so happy about the last two questions because my presentation is basically trying to answer those questions, trying to answer how are we going to account for this natural carbonation and also the accelerated carbonation that we are having in our materials. But before starting, I want to acknowledge the two universities that basically allow me to do this research. The first one, my current one, that is Texas State, and also my former one, Purdue University, with my former PhD advisor, Professor Belay, and also my colleague of mine, Dr. Brito Francioso, and also the PhD candidate, Marina, that helped with all this research, okay? So my presentation is gonna have like different points. First, I'm gonna do like a background and also motivation of it. Then I'm gonna present like the procedure that we follow. We are gonna show like some results and some discussion. And then finally, we are gonna see like the conclusions of this, okay? So as human beings right now, we are facing one of the biggest challenges that in humanity, that is basically dealing with the CO2 emissions that have been increasing for the last like 50 years like crazy. This is causing a lot of problems in the world. That is basically because we have the highest level in the last 3-5 million years. And this is causing, as I said, like different problems like climate change or air pollution. Like we have more than 7 million premature deaths per year because of all the pollution that we are receiving, NOx gases and all these things. We are also dealing with a waste production issue. We have more than 2 billion tons of municipal solid waste, but also like concrete is dealing with that, and also natural depletion. That there, like some experts estimate that there is going to be almost no fish in 2050 if we follow on these trends. So we are going to try to change this, okay? So like the question now is like, is this going to change? I don't think so. Because basically our population is still increasing all the time, so we are having more people. More people basically is telling us that we will need more things. We will have more impacts in the future, right? So if we don't change something, this is basically going to go on against us. So here I showed the United Nations have like 17 goals, and if you focus more, probably you cannot read anything, but like 40% of them are directly related to sustainability, okay? It's not that I want to put it in that way. It's like they are basically saying we need to make everything more sustainable. So basically, this is telling us that this is a top priority, okay? So now the question is, so I'm speaking about general things. How is this related to concrete? So concrete is made out of these materials, right? Aggregate, cement, water, admixtures, and other things. One of these materials that also the other speakers spoke about it, cement is basically producing more than 8% of the total CO2 emissions, and also the aggregates that normally we use more than 10 billion cubic jar of aggregates every year. That means a lot of natural depletion, waste generation, as I was saying. But I don't want to say that we have a bad material, okay? We are all concrete freaks in a way. So concrete is a good material that can be used to build like different buildings like Hoover Dam, Guggenheim Museum, and everything. Indeed, this is the second most used material in the world, only after the water, with more than 30 billion tons produced each year. What does this sentence mean? This means that if we reduce only a little bit of the environmental impact, we will make a huge impact in the world, right? So that is basically our purpose. So as also the other speakers were saying, the cement-based materials are known for sequestrating some CO2. And indeed, like some research quantified that 43% of the CO2 produced in this period of time, so in these 70, 80 years, were uptake by the cement elements, okay, the concrete elements. We know that there are like two ways of updating CO2. One is passive, so natural carbonation, the typical carbonation that we all hear about, and then the active one. The active one is using like CO2 curing, using carbon cure technologies like CO2 liquid inside the mixer. And depending on the concrete that we have, the problem with this is like we will have different CO2 uptake rates. Okay, like different permeability will lead to different injection to CO2 inside the material. So in that case, we cannot quantify that. And the problem is like the traditional methods that we use, that is basically the life cycle assessment, only have two ways. One that is cradle to gate. So it's a picture at year 0. So you produce the concrete, you estimate the CO2 emission, and that's it. And then cradle to grave. That is a picture at year 100. So you have one picture here, one picture here. The problem is what happens here. Okay? So like the big question here is what is the imbalance? What is the imbalance between CO2 emitted and CO2 uptake? For example, if you, what is better, like emitting a lot and uptaking like super fast, or emitting less at the beginning and then uptaking like little? So to put another real example is like, imagine that you have a house or like a building, any building, and then a fire happens. You have one picture here, one picture after, right? So, but probably this is not enough to understand what happened. So like what is happening during the fire, okay? What is happening in the service life of the material. So in order to do that, we use like 3 different types of concrete, normal mixers, one with 100% OPC, with fly ash, and then with slag concrete, and we assume different things. We use a functional unit of 1 cubic meter of concrete with 30 megapascals compressive strength, and we estimate the mix design based on different things. So we assume that all the concretes will have the same compressive strength with the same water to binder ratio based on the replacement of the admixtures. Also, we obtain the water to binder ratio using like well-known formulas like Abrams or Bolomé. We use 25% of paste, 75% of aggregate, 35 fine, and 40% coarse aggregate. And then we did like volume substitution of the supplementary cementitious materials. Okay? So these are our assumptions. Then we first calculated the global warming potential at year 0 with different like data that we use, EcoInvent and other also previous journal. And then we estimated the global warming potential, or in other words, CO2 emissions of all these countries at year, or all these concretes at year 0. Okay? Now we also can estimate at year 100. We assume that at year 100 the carbonation will be completed. That means that their theoretical CO2 maximum CO2 uptake, that is basically also what the other speakers were speaking about, that is based on this formula right here, that I'm not going to explain it, but it's the Steiner equation that basically tells you with the composition of your cement or your cementitious materials is telling you what is the maximum that you can take. That is around a 50%, as also we were speaking about. So at year 100, we're assuming that all the concretes are going to be completed carbonated. That I think that is a realistic assumption, right? And well, this is the equation that is basically subtracting the maximum CO2, okay? The sequestration. So what's happened in the intermediate years? In the intermediate years, we all know that the carbonation is related to is direct proportional to the square root of time. So in order to calculate what happens at year 1, 2, 3, whatever, we use this equation right here. But at this point, like what happens with the different CO2 uptake rates? Okay, how do we account that? So for that, we assume 3 different types. The one that is weathering carbonation, conventional carbonation. Then another one, in a previous study, we saw that there was an acceleration of CO2 uptake due to nano-modification. That means that we added nanomaterials into the mix, and we were able to accelerate the CO2 uptake. So that was our second concrete. And then the third one is like a CO2 cure mixture. And based on previous studies, we assume that the CO2 uptake during the CO2 curing or CO2 mineralization, it was around 15%. Okay? So we are going to basically use these 3 concretes to estimate what happens with the CO2 uptake rate. So for that, we included a factor here that is Ka, that is basically the accelerator factor. Okay? It's going to be 0 for conventional and also for CO2 cure concretes. And the question now is like, what happens with the nano-modification? We only measure like 7 years, the first 7 years, well, 6.8 years, but like, what is going to be this value? Okay? So for this value, here I show global warming potential on the y-axis, and then year. Okay? So we measure the black curve there. Okay? So like there are, and we need to finish here because we assume that we uptake the maximum one. Okay? So what happens in the middle? The question is, what happens? I don't know. So since I don't know, I'm going to do the string situations, and then my solution has to be in the middle, somewhere in the middle. Okay? So the first one is assuming that this acceleration will happen during the whole life. Okay? So it's going to happen during the whole life until it finishes. Of course, it cannot uptake more than the maximum, and then it stays the same. And then the other one is saying, but what happens if we accelerate, then we fill pores, the permeability reduces. So in that case, the CO2 cannot be diffused into the concrete. So like basically what I'm trying to say is like the uptake is going to slow down. Okay? So it's not that fast then during the next year. So the other thing is basically doing like a slow tender to the same point. Okay? So these are the two options. So like as an overview, the modification factor, the acceleration factor will be 0 for this. For the nano-modified will be 0.83 because it's accelerating 83% more. And then for B will be 0.83 for the first, and then 0 for the next years. Okay? And at this point, I mentioned in my title that I was analyzing everything dynamic, but at this point I didn't mention anything, right, yet. So like the question is this static or dynamic? This is over time, right? So that means that this is a dynamic thing, but I didn't include that in the analysis yet. So remember like the analysis, well, the emissions that we showed before, and if you see this picture, you will think it's always the same. So like no matter how fast we uptake CO2, at the end of like of year 100 is like this. So the global warming potential or the environmental impact is the same in both concretes. So my answer, I will say no. Why? Because if you uptake more at the beginning, you are reducing the concentration in the atmosphere. So if you emit a lot at year 0, you can increase the temperature of the wall, for example, like 4 degrees. In comparison to the increasing less, so in that case, like the impacts that you can make on the environment like is much higher. Okay? So in order to account that, what we did is basically instead of using directly this number, we use the dynamic global warming potential. I'm not going to explain this equation, but in the sense it's basically the area under this curve. Okay? So like for example, at year 60, we calculate this area under the curve. And now the problem is, but what about the units? If you say that this is an area, this is kilograms CO2 equivalent times year. So we cannot compare that with the analysis that we have, right? So what we did is basically dividing that by the year and obtaining an equivalent global warming potential. So like you just divide the total number that you got divided by the years that you spent. Okay? So we are going to see what is the difference between both. Okay? So if we plot global warming potential versus year in the first 6.8, that was the acceleration one, using the static and also using the dynamic for the 3 different concretes: conventional, nano-modified, and CO2 curing. We don't have 2 nano-modified because at 6.8 we measure it, so we know what is happening. Okay? So like at the beginning, the blue and the orange one have like 13.4 more CO2 emissions than the CO2 curing. Why? Because the CO2 curing already uptake some of the CO2. Okay? At 6.8, we see that the static, if we compare orange with green, we see that the decrease was 7.2%. But like using the dynamic, the difference was higher. Why? Because the orange one basically emit a lot, but didn't uptake that much. Like what I mean is like the imbalance was higher than the other one because it was the CO2 was emitted to the atmosphere. It was producing effects in the environment, and instead of like the green one that basically released less CO2 at the beginning, so it was much easier with the natural, well, with the atmosphere, I guess. Okay, so this happened in the first thing, but how does this affect the global warming potential in the whole life, in the 100 years? So we do exactly the same thing. I plot here the static values and also the dynamic values with the 4 different ones, the conventional one, the CO2 curing, the nano-modified A, and the nano-modified B. As you can see, all these values are ending in the same point, but none of these concretes are ending on the same point using the dynamic. And also you see that the dynamic normally accounts for higher final CO2 emissions, and is because basically it's taking into account that you are emitting CO2 and you are not uptaking. And that is having an impact on the environment anyways. Even though you uptake it at year 100, you already made an impact. So we need to account for that. So, well, as an overview, at year 100, considering the traditional methods, we will have the same exact value. And using this dynamic methodology, different concretes will have different ones. And for example, one thing that we can focus here is like, even though the CO2 curing had like lower CO2 emissions at the beginning, nano-modified A had lower final CO2 emissions. So accelerating the CO2 uptake during the service life can really make an impact at the end of the service life. All this was about OPC, 100% with OPC concrete. But also SEMs could have an effect. Okay? So we did exactly the same analysis, and we see that the decreases with supplementary cementitious materials were even higher. Okay? Because like the percentage decrease were higher with containing fly ash and containing also slag. Okay? So like if even we include supplementary cementitious materials in this analysis or in this concrete, we are producing even better impacts. Okay? So like the conclusions here are that even though like CO2 cured concrete possess lower equivalent or dynamic global warming potential right after the production, the nano-modified A concretes, that basically the one that accelerates all the time, exhibited the lower at year 100, that the results show that this proposed dynamic analysis successfully quantified the effect of CO2 uptake rate, because like the final value is not the same for all the concretes, and that this dynamic method is only a first step. Why? Because it's only global warming potential. We know that when we are doing a life cycle assessment, we need to account for a lot of different categories, right? We need to account for energy consumption. We need to account for ocean acidification. So like I'm guessing, or I'm hoping that this is gonna be expanded to other impact categories, or even the whole holistic LCA. So in that case, we can do a more realistic assessment of the environmental performance of these materials. Okay? So at this point, I just want to thank you for all, and I will be like so happy to take any questions.